Good morning, class. We are looking at the exam 3 review, covering chapters 3 and 4, differentiation rules, application of differentiation. This exam covers from 3.9 to 3.11 and 4.1 to 4.5. Here's the first part, 3.9, related rates. So in this exam, we're going to cover related rates, linear approximation and differentiations, hyperbolic functions, maximum and minimum values, the mean value theorem, how derivatives affect the shape of a graph, indeterminate form, and L'Hopital's rule, summary of curve sketching. And this is a pledge, I can't emphasize this enough. When you take an exam, you take the exam on your own. Assume you're taking it on campus, meaning no notes, no PowerPoints, no index cards, no formula sheets, no help whatsoever, okay? Differentiation formulas from the definition. F prime of x is limit of f of x plus h minus f of x over h as h, which is 0, or dy dx is limit of delta y over delta x as delta x approaches 0. And we have some basic formulas for the limits, definition of a e in two different forms, basic differentiation formulas, product and quotient rules, exponential rules, composite function resulting in the chain rule, logs, inverse trigonometric functions. So this is the synopsis of differentiation formulas. Hopefully we are very comfortable with, and we are going to move on. 3.9, related rates. If we are pumping air into a balloon, both the volume and the radius of the balloon are increasing, and the rates of increase are related to each other. But it is much easier to measure directly the rate of increase of the volume and the rate of increase of the radius. In a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. What is the procedure? Number one, find an equation that relates the two quantities. Number two, use the chain rule to differentiate both sides with respect to time. Now, the independent variable is t, and that's really the key. dy dt is dy du dt, so the independent variable is t. A warm-up example, air is being pumped into a spherical balloon so that its volume is increased. Its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So we're dealing with an application problem. What is given, what is missing? So first let's explain that verbally, and then we go symbolically. So the rate of increase of the volume is given as, volume of air is given as 100 cubic centimeters per second. What is missing? The rate of increase of the radius when the diameter is 50 or the radius is half of that, 25. So first, spherical shape, looking like a basketball, the volume is 4 times power cube. So we should know the formula for the volume, and D equals 2 times R. So now let's write what is given symbolically. The rate of increase of the volume, that means dV dt. So the volume is 4 times power cube. dV dt is 100 cubic centimeters per second. We are looking to find dr dt when r is d over 2 or 25 centimeters. So the volume is 4 times power cube. dV dt is 100 cubic centimeters per second. We want to find dr dt when r is d over 2 or 25 centimeters. So dV dt, as we want to move from v to t, the intermediate variable is r. Please understand we have two variables, v and r. V depends on r, and r depends on t. So everything depends on t. And so to do so, dv dr dt. So that's what we need to do. Now, first and foremost, when you want to differentiate this, this is a number, this is a coefficient, this is a multiplier, so it doesn't change. So dv dt, you start with 4/3 pi, and now you just work on r cubed with the, which is 3r squared, and then dr dt. 3r squared, and then dr dt. So we have 4 pi r squared dr dt. We replace what we have, and we find the missing one. Of course, you can plug in just the way it is, or you can say dr dt is the left side divided by 4 pi r squared. Replace the dv dt. That's why you write things symbolically. It doesn't matter how long it takes. It makes it a lot easier here. So plug in 100 here, and 4 pi r 25 squared. Now 4 times 25 is 100. So that means 4 times 1 of this cancels out this one. And we get precisely 1/25 pi, which is positive, means increasing. And we also add a rough estimate. So we write the radius of the balloon is increasing at the rate of 1/25 pi, which is roughly 0.0127 units centimeters per second. Units of r over units of t, or if you plug in the units for this one, cubic centimeters per second, and for r, centimeters and square it, you will get the same units. In other words, whatever we do to numbers, we do it to units, it results in the proper unit at the end. A small rock is dropped into a lake. Circular ripples spread over the surface, with the radius of each circle increasing at the rate of 3/2 feet per second. Find the rate at which the area of a circle is changing when the radius is 4 feet. So circle, radius, area. So we should know a piece of information from geometry algebra. We have a circle. From the center to the circle is the radius. From the center, go both sides is diameter. Go around it is the circumference. Diameter is 2 times r. Circumference is 2 pi r. And the area is pi r squared. In this question, since it mentions area, we need which of these formulas? Area equals pi r squared. So we're going to reread the question. And as we read it again, with the radius of each circle increasing at this rate, that means dr dt is 3/2 feet per second. We are looking for the rate at which the area is changing, dA dt, at a precise moment when r is 4 feet. So a is pi r squared. Dr dt is 3/2 feet per second. We are interested in dA when r is 4 feet. So we differentiate this with respect to t. That means the pi remains as a multiplier, a coefficient. So dA dt is pi, and then you're going to differentiate r squared. That is 2r dr dt. And that means 2 pi r dr dt. Replace the r with 4, or better yet 4 feet. Dr dt with 3/2, or better yet 3/2 feet per second, because we can do the same thing with the units. And what happens is these two cancel each other. We end up with 12 pi square feet per second as an exact answer. A rough estimate. You always write the exact. If they ask you for an approximation, you have the exact, and you also write the approximation with proper decimals as they ask you. A 20-foot ladder leans against a building. The base of the ladder slips away at a rate of 2 feet per minute. Find the rate of change of the height of the ladder when the base is 12 feet from the building. Bear in mind, it's an application. And you have to draw the setting. Even if they don't ask you, it's a must. Draw the setting, define your variables. So here's the building or the wall, here's the ladder. It slips away this way, creates the speed or rate d, because we called it x, we're going to call it dx dt. We call this x, this is dx dt, 2 feet per minute. As it moves this way, this comes down and creates a shape which is a right triangle. So this is a right triangle. And this moves down, creating the speed downwards, known as dy dt. Why is it dy dt? Because we call this side y. If you call it a dA dt, whatever you call it, we call this x dx dt. And that, we want to find the rate of the change of the height. You can call it h and dh dt. And the ladder is fixed. How many feet? 20 feet. So we're going to call it C. And we want to find this precisely at the moment when the base x is 12 feet. So dx dt is 2 feet per second. The formula that combines them, Pythagorean theorem, indicates a squared plus b squared equals c squared in general. So x squared plus y squared equals c squared, which is 20 squared. And we want dy dt at the precise moment when x is 12 feet. So this is the translation of the question, of course, with the help of the setting. Dx dt is 2 feet per minute, x squared plus y squared equals 20 squared, or 400. Dy dt is missing when x is 12 feet. So we need to differentiate this with respect to t, with respect to t. So the derivative of x is no longer 1, it's rather dx dt. So this becomes 2x dx dt. This becomes 2y dy dt. And 400 results in 0 because it's a number. Now, we've got everything. So we have the x, we have the dx dt, but we don't have the y. So what is y? At the moment x is 12, put it into Pythagorean theorem and evaluate the y. At that moment, this is 144, 400, subtract 256. The square root is 16 feet. Now we got everything, we're going to plug in. 2 times 12 times 2, 48. 2 times 16 is 32. Move the 48 to the right, make it negative. Divide everything by 32. They're both divisible by 16. Negative 3 halves. So dy dt is negative 3 halves feet per minute. Notice x is increasing, therefore dx dt is positive. Y is coming down, it's decreasing, so dy dt must be negative. And it is. Now, as this moves down, the angle, this one and that one also changes. So in this question, we're going to look at the same situation. A 20-foot ladder leans against a building. The base of the ladder slips away at the rate of 2 feet per minute. Find the rate of change of the angle between the ladder and the ground when the base is 12 feet from the building. In other words, we have the same situation. This is the building or the wall. This is the ladder. As it moves this way, creates the speed of dx dt equals 2 feet per minute, because we call this x, creates the shape which is a right triangle, as it moves down, okay, creates dy dt, creates the change here, creates the change here, and this is fixed at 20 feet. And we are looking at what they are asking us to find. Find the rate of the change of the angle between what? Between the ladder and the ground. So not this one, this one. So we're going to call this theta. And so we want d theta dt. So this setting tells us exactly what needs to be done. So if we were to write this, then we would write dx dt is 2 feet per minute, x squared plus y squared is still 20 squared. But this time we are looking for d theta dt when x is 12 feet. Now, the idea is that you have to define your variables, okay, first and foremost, and we've done that. And now we want to find an equation that relates the two quantities. The quantities are what? We know this one, that means x and dx dt, and we want d theta dt. So we want to relate x and theta if possible. And you can find sine of theta as well as cosine theta. Sine of theta is the opposite, which is y over 20. Cosine theta is the adjacent, which is x over 20. And of course, we are going to use this one because this is the one that relates the theta to the known. So x and dx dt are given. Now, one might say, okay, I know the value of y, I've calculated in the previous page. I know the value of dy dt, that is absolutely right. However, always use what is known just to be on the safe side, because in case we made a mistake previously. So we're going to go with cosine theta, which is x over 20. And please understand this means 1 over 20 times x. So cosine, as you know, the derivative is negative sine. So negative sine of the same argument theta. And then because theta is not the independent variable, t is, therefore d theta dt. And the right side is, of course, 1 over 20 times x becomes dx dt. 1 over 20 times dx. Now, everything is in order. We have dx dt, okay. And we know minus sine theta is y over 20. So let's replace that minus y over 20. And dx dt, replace it with 2. And what we need to find is the value of y, which is, of course, using Pythagorean theorem, which was used, and we found it to be 16. So I'm going to show you again, x squared plus y squared equals 20 squared. We ended up with y being 16. So we can replace the y with 16. And when we do that, please understand, we can get rid of the denominator because both sides have the same denominator 20. So there's no reason to waste time. So we have minus 16 d theta dt equals positive 2. That's what we have. And so d theta dt is 2 over negative 16. 2 over negative 16, or negative 1 over 8. Negative 1 over 8 units of theta over units of time. Units of theta, it is always given in radians in calculus unless otherwise mentioned. So in calculus, units of angles are always theta. And that's important to remember, always. Falling sand is forming a cone-shaped pile. The volume of the cone is increasing at a rate of 54 pi cubic inches per minute. The height of the cone is twice the radius of the base. Find the rate at which the radius changes when the radius is 6 inches. So first, what is a cone? Looks like that with the height, with the radius. and the volume is 1/3 pi r squared h. That is a piece of information from algebra geometry we should know to begin with, because we want to relate the volume to the radius, to the height, whatever. And if the volume is that, it says it's increasing at this rate, meaning dV dt. So the volume is 1/3 pi r squared h, and dV dt is 54 pi cubic inches per minute. The height, twice the radius, so h is 2r, h is 2r. We want the rate at which the radius changes, dr dt, when r is 6. So translation of the question, the volume, that's a piece of information we should have, is 1/3 pi r squared h. dV dt is 54 pi cubic inches per minute. The relationship between h and r is that h is 2 times r, and dr dt is missing when r is 6 inches. Bear in mind, the volume is a function of r and h. So we have two variables here. And if we were to differentiate to find dV dt, you have to use the product rule. However, because h equals to r, replace the h with 2r or r with h over 2, depending upon what they ask. Because they are asking for dr dt, we want to keep the r, we want to get rid of h. If they were asking for dh dt, then you would keep the h and get rid of the r, either way. So to get rid of the r, h over 2. To get rid of the h, 2r. So replace the h first with 2r. So the volume is 2/3 pi r cubed. Now you want to differentiate this. dV dt and 2/3 pi is just a number. So this is not going to do anything. It's a multiplier. It's a coefficient. So what do we need to differentiate? Just r cubed, which is 3r squared dr dt. In other words, 2 pi r squared dr dt. Now plug in. dV dt is 54, so replace that 54 pi. 2 times pi times 6 squared, or you can solve for dr dt by dividing by 2 pi r squared. It doesn't make any difference. Just either plug in right here or solve for dr dt. 2 pi r is replaced with 6, square it. So when we square this, we get 36 times 2, we get 72. So we get 72 pi dr dt, and dr dt would be 54 pi divided by 72 pi. Of course, pi cancels out the pi, and they both are divisible by 18, 3 over 4 units of r over units of t, 3/4 of an inch per minute, or you can put the units here as well as here. It will give you the proper one. 3/4 of an inch per minute is the answer. At noon, ship A is 150 kilometers west of ship B. Ship A is sailing east, and ship B is sailing north. So ship A is doing 35 kilometers per hour, and ship B is doing 25 kilometers per hour. That's their speed or rate. How fast is the distance between the ships changing at 4 p.m.? In other words, from noon to 4 p.m., we're talking about t equals 4 hours, just to give you an idea. So this is impossible to do without the drawing, because the setting is a must. So here's the setting. At noon, we start here. Let A sub 0 be the position of ship A, and let B sub 0 be the position of ship B. So this is where ship A is. It's moving this way to the right because it's going east, and B goes up to the north, and their distance is originally 150 kilometers. And this is doing 35. kilometers per hour. This is doing 25 kilometers per hour. So A moves east at 35 kilometers per hour. Let X be the distance traveled by A at time t. So it moves some distance at time t. So moves and gets here. Similarly, B moves north at 25 kilometers per hour. Let Y be the distance traveled by B at time t. So at any moment, this is going this way, this is going up. So it creates this distance, this distance, this distance, this distance. That's what we are talking about. So this is X. Therefore, this must be 150 minus X. This is Y. We're going to call this something, for example, Z. Now what's happening? dx dt, we said the speed or rate is 35, of course, kilometers per hour. dy dt is 25 kilometers per hour. A has sailed east x kilometers. The remaining distance is 150 minus x. So this is x. This must be 150 minus x. So as it moves this way, it creates the speed or rate dx dt is 35 kilometers per hour. As B moves up north, going that way creates the speed of dy dt equals 25 kilometers per hour. And therefore, we are interested in this, how fast the distance is changing, and we're going to call it dz, dt, 4 hours later. From noon to 4 p.m. is 4 hours later. So we are going to write dx dt is 35 kilometers per hour, dy dt is 25 kilometers per hour, t is 4 because from noon to 4 p.m. And we want to find the missing dz dt. We have to make up an equation. And from here to here to here, this setting will give us the Pythagorean theorem, a squared plus b squared equals c squared. So a squared plus b squared equals c squared. A is 150 minus x, so quantity squared, plus b, y, quantity squared, equals z squared. So I hope you see this last drawing gives rise to the equation, and the rest of it becomes elementary algebra after the very first step, which is differentiation. So we differentiate, and then everything becomes elementary algebra. This comes from Pythagorean theorem for this one. Okay. And so, in other words, a squared plus b squared equals c squared. And so let's differentiate. This one is 2, 150 minus x to the power of 1 times the derivative of the inside, which is minus dx dt. So 2 times 150 minus x times the derivative of the inside minus dx dt. This plus 2 by dy dt. This equals 2z dz dt. So we want to plug in everything that we have. So we have to find x and y and z. We have x, the distance. When we do 35 kilometers per hour, x would be 4 times 35. Y would be 4 times 25. So x 4 times 35 because at 4 p.m. Y is 4 times 25. And we have 140, 100. And now for the z. To find the z value, you have to plug it in here. Replace the x with 140, y with 100 to find the missing z. Obviously, 150 minus 140 is 10. Square root is 100. This one square root is 10,000. So z is the square root of 10,100. I hope it's clear to everybody how we arrive at each, right? And so we plug in 2 times 150 minus 140 times minus 35 plus 2 times 100, which is y times dy dt, which is 25. And the right side is 2 times this number, the zdt. And we put the number just the way it is for now, ultimately. Because remember, if you want to do the rounding, it happens at the end if you need to do that. So this is obviously, we see the 2 and 2 and 2. Let's actually drop them because you can factor the 2 out from both sides, get rid of them, no reason for that. So 150 minus 140, 10. 10 times negative 35 is negative 350. 100 times 25 is 2500. And if you add these two numbers, you get 2150. So divide 2150 by the square root of 10,100. That becomes the ZDT. Now use a calculator. And however many decimals that they ask you, in this case, I'm using 1 decimal, but please make sure you put as many decimals as they ask you, 21.4 kilometers per hour. A spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks from the spotlight towards the building at a speed of 1.6 meters per second, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? Impossible to do without this setting. So what do we have here? Somewhere here we have the spotlight, somewhere here we have the ball, and we are going moving towards to the wall. What is this distance? 12 meters. Which way are we moving? This way. So over here, we have the light. The man is moving. This is the wall. So here's the light. Here's the man. Here's the wall. And the man is 2 meters tall. 2 meters tall. Now, bear in mind, if the man is standing here, there is nothing to show. But as the man moves, okay, the light hits the back of the man and it creates a shadow. Now, if this guy is here, for example, just so everybody can see, if he's here, the shadow is up here. If the guy is here, the shadow is here. So clearly, the shadow must be decreasing, right? So if this distance is x and this entire thing is 12, then this distance must be 12 minus x. Let me erase my work. I just wanted to show you how things happen here. So when the man covers x feet, his speed is dx dt. So going this way, dx dt is given as 1.6 meters per second. And the shadow covers y, and his shadow speed is dy dt. as it gets smaller, the shadow gets smaller, dy dt is decreasing, and that's what we are looking for. Now that we have the drawing, here's the synopsis. Dx dt is given as 1.6 meters per second. Dy dt is missing at a precise moment when x, so we are 4 meters from the building. So 12 minus x must be 4. 12 minus x, 4 meters from the building means 12 minus x. So x must be 8 meters. So at the moment when x is 8 meters. So they didn't give us x, they did give us 12 minus x. Okay. So we notice this, there are two triangles here, the small one and the large one. They are similar triangles. So what do we know about similar figures? For similar figures, corresponding angles are identical or equal. Corresponding sides are in proportion. So why are they similar figures? Look at this angle. It's common and therefore identical. This angle and this angle are both 90 degrees. And these are equal. By the way, when the two lines are parallel, these two angles are equal, these two angles. All angles are identical, and that makes similar figures. And so x late x, y, right? Similar figures. So, for example, we can say the relationship for the large one, y, to 12 is the relationship for the small one, 2 to x. Again, that's one way to write it. There are different ways of writing it. So the large triangle, the base is y, and let's say this is the height. It's 12. The little one, the smaller one, the base is 2, the height is x. And so now we are in business. We are interested in solving for y. Y is 2 times 12 divided by x, cross product, right? And to differentiate that, let's rewrite this as 24x to the power of -1. So it makes it easier to differentiate now. 24. Let's actually do these steps. So if I want to differentiate this, I'm going to write it here. dy dt is 24 times -1 x to the power of -2, and then dx dt. Now, 24 times -1 times x to the power of -2 is this one. And times dx dt. Okay? And so let me erase my work. And so dy dt would be -24 over x, which is 8 squared, dx dt, which is 1.6. This is -3. This goes away. And I hope you see that 1.6. Imagine that 16 divided by 8 would be 2. 1.6 gives you 0.2. So negative 0.6 meters per second, units of y over units of time, which means the length of his shadow is decreasing at the rate of 0.6 meters per second. You don't mention the negative anymore when we say decreasing, everybody. A cylindrical tank with radius 10 meters is being filled with water at a rate of 7 cubic meters per minute. How fast is the height of the water increasing? Draw a diagram, include units. Again, you have to do that. You're talking about a cylindrical shape with the radius being 10 meters. We should know the radius, okay, and this is being filled. That means the volume. The relationship is that the volume is pi r squared h. Pi r squared h. What is this? dV dt. 7 cubic meters per minute. And of course, r is fixed at 10 meters. How fast is the height? The h dt is changing. We should really say changing. Positive means increasing, negative means decreasing. So the volume is pi r squared h. dV dt is 7 cubic meters per minute. R is fixed at 10 meters dH dt. So there are a couple of different ways to handle M class. Number one, we can just differentiate this dV dt, and pi r squared is fixed. The reason pi r squared is fixed because r is fixed at 10 meters. R doesn't change. Going up and down makes no difference, okay? So pi r squared is a number times h, now dH dt. So I can replace this with 7, a capital R with 10. Of course, this is 100. So we are looking at 100 pi. So dH dt is 7 over 100 pi meters per minute. This is an exact answer, everybody. And let's keep it as that. If they ask for an approximation, you can always do that. We could have replaced the r here with 10, and that's pi times 10 squared, or 100 pi h. And then if you differentiate this again, you keep the 100. dV dt is 100 pi. So this you keep. H becomes dH dt, and that's exactly what you have here. Perhaps this would be a faster and better way. I'm just showing you different ways. Okay, either way is fine. If the minute hand of a clock has a length r in centimeters, find the rate at which it sweeps out area as a function of theta. If they don't give you the units, then you can't give back the units. That's all the difference. So I want to remind you, this is a circle. This is central angle theta. This is the radius r. And we have this arc length s equals r theta, and this area half of r squared theta. So this is a piece of information from trigonometry. This area is 1/2 r squared theta. And this arc length is S. Okay. So we're talking about the area, everybody. We're talking about the area. Area is 1/2 r squared theta. So this is what we're going to do. The ADT, and R is fixed because the length of the minute hand or the hour hand or the second hand is not going to change. So R is a number in essence, whatever it might be. If you have it, you replace it. So we want the ADT. That's the idea. So find the rate at which it sweeps out the area. So we want the ADT. So the ADT is half of R squared because that's a number. That's is a number, so it's not going to go times what? Now theta, d theta dt. That is the variable theta. And theta is uh, depends on t. And believe it or not, you're done. But just to have a better understanding of this concept, as an example, if we go for 1 hour, so a minute hand, as you know, starts and it covers it completely, a complete cycle, okay, a complete revolution, 360 degrees or 2 pi radians it covers over the course of hour. So 360 degrees, the theta dt is 2 pi radians per hour. So this can be replaced with 2 pi. So half of r squared times 2 pi, 2 cancels out the 2. You get pi r squared, okay? The units, cubic square centimeters per hour, pi r squared, square centimeters per hour. So the units are important, class. Pi r squared, centimeter squared per hour. Another example, if we happen to deal with 1 day, which is 24 hours, that means it goes around one revolution for 1 hour. For 24 hours, it goes 24 revolutions, 24 times 360 degrees, 24 times 2 pi radians per day. So replace it. So replace it with 24 times 2 pi or 48 pi. So this one, we are going to replace it with 48 pi radians per day. So half of r squared times 48 pi becomes 24 pi r squared centimeter squared per day. A street light is mounted at top of a 15-foot tall pole. A man 6 feet tall walks away from the pole with a speed of 5 feet per second along a straight path. How fast is the tip of his shadow moving when he is 40 feet from the pole? Again, I can't do that without the drawing. We have to draw the setting. So look at the setting, everybody. So 15 feet of pole. The man is 6 feet. Moving this way with the speed or rate of dx dt 5 feet per second. We are going to define this one as x in a moment. And this one, see, as it, first of all, if it's here, there is right here, there is no shadow. As he moves away, okay, the shadow is created and the tip of the shadow is here. So when the man covers x feet, that means this is x, his shadow covers y feet. Dx dt, the speed of the man, is 5 feet per second. Dy dt is of interest to us because look at how fast is the tip of his shadow moving. At what point? When he's 40 feet from the pole, when x is 40 feet. So the man moves that way. Let's say speed of dx dt or 5 feet per second, y, and we are interested in dy dt. So let's do the drawing. Understand that this is also two triangles that are similar. So the small one and the large one are similar. where this distance is x, this distance is y. And so please understand then this distance must be y minus x. And so if we say compare the small one to the large one, 6 over 15 is the same as y minus x over y. In other words, 6 from the smaller one, 15 from the larger one, y minus x from the smaller one, and y from the larger one. And that's all. As long as you have this one, practically you're done, because now you are going to solve for y and then differentiate. To solve for y, we're going to do the cross product. 15 times y minus x is the same as 6 times y. 15y minus 15x. We're going to move this one, make it positive. Move this one, make it negative. We get 9y. And then divide both sides by 9. Drop a common factor of 3. Y equals 5/3 x. Which means dy dt is 5/3 dx dt. So dy dt is 5/3 times 5, 25/3 feet per second. So it's pretty straightforward, everybody. A spherical balloon is deflating, losing 8 cubic centimeters of air per minute. At the moment when the radius of the balloon is 20 centimeters, how fast is the radius changing? Again, reminding you, here's the spherical shape, here's the volume. You should know that. So the volume is 4/3 power cube. And we need that because we're talking about losing air. That means dv dt is, now this is the thing, minus, because it's losing. If it's gaining, it's positive, minus 8 cubic centimeters per minute. And at the moment when the radius is, when r is 20, we want to see dr dt. So symbolically, the volume 4/3 power cube. Given dv dt is negative 8 cubic centimeters per minute, dr dt is missing when r is 20 centimeters. So let's differentiate. And we've done this before. So dv dt is 4/3 pi, because 4/3 pi is a number. It doesn't do anything. You keep it as a product, as a multiplier, as a coefficient. R cube, 3r squared dr dt. And let's make sure this is uppercase also, because it's uppercase. And so these two cancel each other. 4 pi r squared dr dt. Let's plug in r is 20 and square it. Dr dt missing, and dv dt, plug it, negative 8. Now 20 square it, 400 times 4, 1600 pi. So we have 1600 pi dr dt, divided by 1600 pi, and 8 goes away, becomes negative 1, 16 becomes 2, so 200 pi. So negative 1 over 200 pi, units of r over units of time, centimeters per minute. And if they ask you to do the approximation, they will ask you how many decimals, then you put it roughly, in this case, minus 0.001592 centimeters per minute. And what does that mean? The radius is decreasing at the rate of 1 over 200 pi. I use the exact answer, centimeters per minute. Bear in mind, you don't mention the negative because when you say decreasing, it takes care of the